So welcome to lecture number 15. In this particular lecture, we already have seen the four postulates. In this lecture, let us start with an example problem. So let us consider in this example, consider a particle in a box within 3D quantum mechanical system. Okay. So you can assume Cartesian coordinates. Check coordinates. So first and foremost, we need to determine the operator corresponding to z component of angular momentum. Okay, fair enough. And B will be, what will be the mean value of expression for the mean value. Mean value of C component angular momentum. All right, so let's look at A, the problem. Number A, what is angular momentum? Angular momentum is R into P, P being the linear momentum. So if you put this in a matrix form, Jk is Cartesian, x, y, z. R has a form x, y, z, and this is Px by the x component of the linear momentum, Py and Pz. All right. Okay. So the z component angular momentum will be Lz. Okay, Lz, which is nothing but x Py minus y Px. That is just from the matrix manipulation. Take it like this, so that is what it is. Okay. Fine. Okay, so as per postulate 1, we have to find out the operator. So we have to find out Lz hat, the operator. So from postulate 1, the operator will be R minus I h bar, okay, x d by dy minus y d by dx. This is the operator. This comes from your postulate 2 that we described. Okay, so this is the expression for the operator for the linear moment, for the angular momentum. Okay, that is a quantum mechanics, the Hermitian operator. So therefore, now if you have to find out the mean value for the C component of angular momentum, L, C, or L rather, C. Okay, what we do is that you basically find out the average of this Z component of the angular momentum. So this is given as star. Lz is the operator function. This acts on psi into d tau, tau being the volume. So in essence, dr is basically, it's a triple integral. Psi star Lz hat psi dx dy z. Okay. So if I now substitute the operator value, this is the operator, right? So Lz Z bar will remain as minus I H bar triple integral I star x psi by dy, right? D psi by dy minus y d psi by dx dx dy dz. Okay, so this is the mean value, and this is given when you substitute for the quantum mechanical operator. For the operator, the form of the operator. So this gives us this enormous power that, you know, this is how you should solve. For example, if you want to find out the mean value of this component of angular momentum, then this is the way you calculate it. Remember, it is the operator is acting on the wave function. So here, right? Okay. Now let us take a next journey will be the steady state. The steady state Schrodinger equation. The steady state. Okay. So what are the things that we know about the Schrodinger's wave equation? First, it can be cast as an eigenvalue problem. In this eigenvalue problem, the wave functions, okay, the eigenfunctions, constitute an orthonormal set of basis functions. Eigenfunctions constitute an orthonormal set of basis functions. The eigenvalues they designate discrete energy levels. Okay, so this was what we knew. This is what we thought. Okay, so also if you look at it carefully, we saw that this prediction of energy levels, using the Schrodinger's wave equation is very well connected or affiliated with, you know, with the classical energy conservation. Okay. So what we are saying is that Schrodinger's wave equation is used for prediction of energy levels that we have seen already. Now, this has got some connection with the classical energy conservation principle as well. Okay. So let's do a very quick verification of this by considering a conservative system. Consider conservative system. Okay. And it can be where by conservative system we mean the potential function V is a function of Cartesian coordinates, Cartesian proposition. Okay. So if I look at it now, the resultant Hamiltonian in normal parlance is given as T plus V, which is equal to, okay, 1 by 2m if it's a three-dimensional system, px squared plus py squared plus pz squared plus b. Right. So the operator, again from postulate 2, which we just did a few moments ago. Okay, so h bar, the operator becomes minus IH square d square dx square plus d square d square plus d square d square plus v. Okay, so the operator essentially becomes h bar square minus 5 2m. Sorry, it's the 2m here. 2m, the Laplace plus v. Okay, plus okay. So therefore, as we can see that this is the operator, this is the corresponding operator. Okay, now we know the Hamiltonian, which is basically like the total energy, and this is the operator h hat. Now, if you look at it, so this is the operator function that we have. So this is already, we knew about this operator. If you recall the past lectures, that the Hamiltonian operator we said is going to be minus h square by 2m Laplace plus v. This we knew. This was already posited. Already stated in earlier lectures. Okay, already stated in earlier lecture. Okay. So, but because potential energy is only a function of position, okay, so it is just the function itself, which is multiplication by v. Okay, since v is only a function of position, so the operator was is simply multiplication by v. Right, simply multiplication by v. Now, we also know that h is nothing but the total energy. Okay, so therefore, your postulate 2, but the fourth point in postulate 2, if you remember the fourth point. Fourth point of postulate 2. Okay. Fourth point of postulate 2 says that the operator corresponding to total energy is IH bar by dt. Right? Okay. And H is equal to E, because that is the H is the total Hamiltonian. Correct? So so now if you look at the form that we have already said, so postulate 2D, if we apply postulate 2D, you will now see this expression becomes 2m square phi r comma t plus b is only a function of r phi r t. Because now this is applied on the wave function. Okay, this is equal to pi h, because that is the total energy now, pi r comma t divided by dt. So you see, this was the wave function, and this was the total energy operator, because h is E. So in one case, the operator acts on H, on E, so we get this. And the left-hand side is the standard operator that we derived. Okay, this is the Hamiltonian operator that we derived. Okay, so this proves the point that if you look at this particular equation now, okay, this produces, this is exactly Schrödinger's wave equation, correct? Wave equation. But how we have done it? We have done it from the energy conservation, right? We started with this. Right? We started with this. Right? So that is the energy conservation that we said. So in essence, what we have seen is that, okay, the Schrodinger's wave equation actually embodies the conservation of energy. Okay, it embodies conservation of energy for a single particle, for a single particle in atomic molecular system. Okay, all right. So this is one of the most illuminating part, that this is how the Schrodinger's wave equation can be cast, and this is how this embodies conservation of energy. So just to give you guys one more thing, in case you guys are kind of worked on this, so therefore this should be equal to, whereas this is the same as this. Okay, so because basically you have applied, so this operator function is nothing but this. So this should be absolutely clear to you. So this embodies the conservation of energy principle. Okay. Now we are in a position to tackle the steady state Schrodinger's wave equation. Okay, so steady state. We started with this, we got distracted a little bit. Steady state wave equation. Okay, so psi r comma t is equal to psi r. This is like a separation of variable. This is the steady state wave function, which is dependent only on position. Dependent only on position. Okay, space basically. Okay, now h hat, when it acts on the wave function, equal to I h bar d psi by dt. This we already know. Therefore, h acting on I r and t, I h dt. Okay. H okay. Something like this. Write it like that, then this will be something like this. So this psi r basically comes out and goes to this side. This comes to this side. Okay. And this must be equal to, because this side is a function of time, this side is a function of space. So therefore, this should be equal to a constant. That is the only way that this equality can be attained. Now, if you look at this part now, only this part of the wave function, you'll find that Tt is given as exponential minus I omega t. Okay. I omega t, where omega is equal to k by h bar. Therefore, E is equal to we already know as h omega is equal to k. Okay. Omega is k by h bar, and energy is nothing but h bar by omega, as we know. Okay. So that is equal to k. All right. So therefore, psi r comma t is equal to psi r into exponential minus I t h bar. This is exponential omega. We are substituting omega by by E by H bar essentially. So that is the total expression that we are getting here. Okay. Okay. Now the spatial portion. Now if we just look at the spatial portion, then becomes H bar I R equal to E. This is a spatial portion. Okay. The spatial portion. So therefore minus h square by 2m. We're just putting in the numbers psi r plus v psi r equal to E. Okay, so it's for a single particle. This is the steady state SS wave equation. Okay, so H bar therefore is written as psi star. I'm just putting the R so that it is easier for you to differentiate. Both can use a different notation, but we are going to stick to this because in writing you cannot replicate such notation. Okay, so H bar, okay, is nothing but the total energy R E. So that's what it is. E is the operator. E tau divided by so you can see the average Hamiltonian also undergoes quantization. Okay, so the average Hamiltonian also undergoes quantization. What happens in this, that the Hamiltonian that you saw, that this now therefore provides the discrete particle energies. Okay. This is the total operator, energy operator, only for steady state systems. For time dependent systems, we still use H bar by T as the total energy operator. This comes from your postulate 2. Postulate 2, number 4. Okay. So this is like the average value, average observable value of any dynamic variable, which is explicitly independent of time, can be. So the average value of any dynamic variable, okay, which is independent time can be solely expressed in terms of steady state wave function. Steady state wave function psi r, which is not dependent on time. Okay. So in essence, that can be written as, this is like a master template. E is the operator. We are, this is R. Okay. So this is the average observable value. So this is like a master expression. Master expression. Okay, this is like a master expression for calculating expectation values. Expectation values. Expectation values for not for, but in terms of the steady state wave function. I mean, for steady state systems in general. Systems in general. Okay. And it undergoes quantization, and we have seen that, you know, temporal information in certain cases are very relevant, because we may want to produce steady state expectation values for various particle properties. Steady state expectation values for various particle properties. So this allows us to do that, because we may not be interested in the temporal space at all. Okay. So this provides us with a unique idea of how you can actually do this. And we have also seen that the Schrodinger's wave equation also embodies the conservation of energy as well. And we have seen what will be the different operators for, say, energy, for angular momentum and stuff like that through that example problem. We'll have a full class where we will cover all these Hermitian operators. And so we can cover more in-depth analysis of that as well. So in the next class, we are going to look at probably multi-particle type of a system. So multi-particle systems, which will be interesting. So multi-particle systems and particle in a box and stuff like that. So we will do that in the next class. Thank you.